So what do we mean by micro and nanotechnology? So there's lots and lots of definitions out there for micro and nanotechnology. One I use, which is pretty loose, because in fact micro and nanotechnology isn't a single technology, it's a whole raft of different technologies that really manipulate matter on a very small scale. So typically for microtechnology, we're talking about active products or devices where the active structures are less than 100 microns in geometry, so they're pretty small. Already about 100 microns is about the diameter of a human hair, so you're already talking about things that are smaller than a human hair, so very difficult for us humans to interface with. When we go into the world of nanotechnology, we're talking about products or devices where some of the active structures are less than 100 nanometers in dimension, so they're extremely small, more on the scale of molecules than on the scale of physical objects. So again, things that we find difficult to interface with in the real world. So in terms of conventional energy, then, what are the sort of micro nanotechnology products that might be of interest? I've thrown up a few examples here. First one on the top left is a real product. In fact, it's not used in conventional energy. It's actually a gyroscope that's used in a cell phone. But there's a lot of interest in being able to collect geographically correlated information using some sort of inertial measurement unit or position sensor. And this is the kind of technology that could help fulfill that if applied in the clean energy space. In the bottom, so these devices are micro devices. The typical structures here are a few microns in geometry, and they convert mechanical movement into electrical energy. On the bottom here, I've shown a different device using exactly the same principle, but in reverse. It converts mechanical movement into electrical energy, but it's used to extract energy from the environment. So this is a little simple inertial energy harvesting device, and this is another area that's been receiving a lot of work in clean technology. This is a mechanical energy harvesting device. We've heard a little bit this morning about solar technology for energy harvesting, and there are many other approaches that are electromagnetic energy harvesting devices and so on, many of which rely on either microtechnology or nanotechnology. Other areas we're working in, for instance, are the packaging of very small systems in a package. So this is an example of a laser system in a package. This one is being used for gas detection remotely from across a large area in an industrial site, so we can actually control and detect the leaks of unwanted gases into the industrial environment. Is that better? Okay, and I feel like a singer now. The next device is another area we work in, which is microfluidics. This is one I've been involved with for quite a little while now. This is a lab on a chip. In this case, this is a sensor device. It's actually a biomedical sensor, but it could equally well be used in the environmental space. And in fact, people are looking at using lab on a chip device to detect unwanted bugs in the environment. Another micro area we work in is in microassembly, and here we are building some very, very robust, very rugged ceramic-based assemblies of electronics and resistors, capacitors, integrated circuits and sensors to create remote autonomous sensors that can be put into harsh environments. And again, the main driver for this at the present in Alberta is the oil and gas industry, where people are trying to extract oil and gas more efficiently and want to be able to instrument the bottom of an oil well, which is a pretty rugged environment. These are all kind of microtechnology type applications that we work with. I've included a little bit of nanotechnology. We don't do so much nanotechnology. Nanotechnology, as we've heard this morning, is the chemistry. It often uses interesting chemistry or interesting biology to generate molecules that have specific functionalities. And so people are using them to make solar cells, for instance. The molecules themselves are not particularly useful. They have to be assembled into working devices, and that's kind of where we come in. We see ourselves working in that area of helping people to build functional devices that can be used as real products. So one of the areas we're working quite a lot with nanotechnologists, in fact, is in the area of lab on a chip, where people want to be able to do assays or using some new clever molecule that can detect, say, a biomarker in the environment, and need somehow to hold that molecule in place, introduce a specimen to it, do some processing, then interrogate the molecule to see what the result is, and that can all be done with a lab on a chip device. So why do people want to use micro nanotechnology in the environmental and the clean energy space? Well, it lets you do new and potentially some very useful things. It lets you do tons and tons of new things. Some of the ideas aren't as useful as others, but as we've seen this morning, there's some really good ideas out there now starting to emerge. One of the key things it lets you do is shrink existing functions, making things smaller, lighter, lower power, more portable, so you can take instrumentation out to the point of use. And that's really a very big area of activity for us, instrumentation and sensors being taken out to the point of use, and analysis to the point of use. Distributed sensor arrays, we've talked a little bit about that, being able to put out a whole array of sensors and figure out what's going on in the environment, monitor unwanted intrusions of chemicals or bugs or whatever. You can also do clever things like if you started, as you're pretty aware now, your cell phone is getting smarter and smarter all the time. That's thanks to micro and nanotechnology. You can now integrate more and more functions into one device, so you get not just a very simple device that does one thing, but devices that can do multiple things at once and give you multiple inputs to better understand what's going on. They have their place in clean energy. We've talked about energy harvesting, and I think that's going to be a big area for micro and nanotechnology. And manipulation at the molecular level, which is we've seen some interesting stuff on self-assembled molecules and exciting things we can do there as well. Micro and nanotechnology is great, but when you actually practically try and take it to the market, there are quite significant challenges. As we've pointed out, micro and nanotechnology devices on their own are not very useful. They have to be assembled into something that actually works in our macroscopic world. Technologies are often very new, and many of the supply chains for these technologies are not established. So it's all very well, you can get your very clever molecule, but then you've got to build a whole bunch of other things around it to actually turn it into a useful device, and building those supply chains is difficult. As you've seen hinted at this morning as well, the technologies are usually cross-disciplinary, multidisciplinary technologies. So you need to bring together people of disparate disciplines, engineers, chemists, biologists, who don't often naturally talk to each other. So you've got to get them to talk to each other and work as teams. Very often the technology itself needs reasonably leading edge manufacturing capabilities. This is not that's its very nature. It's new technology. The manufacturing capabilities themselves are not mature and established yet. The other side we experience quite a lot is that market pool can be quite weak for new technologies. You're often trying to displace an existing technology that's doing quite a good job already. So you've really got to get these technologies out there into the marketplace, get them engaged with the end customers. And because they're new technologies, because they're cross-disciplinary, because they're quite expensive, there's quite a high cost and risk in bringing new products to market. And that kind of discourages a lot of people from, and makes it difficult for new emerging companies to be successful in the existing markets. So ACAMP was really put together to address all those issues. And this is what we try to do. So we work between typically the research base. We work with all the spin-outs that are emerging out of the research base and some of the more mature companies to help them develop new products that can fit into the end, that will find a successful place in an end market. And we provide a bunch of different services that we think are needed to help that happen. So we'll start working with people on product and market definition. What is it they're really trying to make? What markets they're really going to address? How they're going to do it? How they're going to get money for it? And more importantly, then some of the technologies of product development. And one of the big holes that exists in the MNT supply chain is that ability to take the raw device and turn it into a finished product. So we do a lot of work on assembly and packaging. So we were founded, we have a mandate, we're funded by the government. Our mandate is to help Alberta grow a globally competitive critical mass of commercial MNT device and technology companies. So we're here to help lots of different people. I've got 2 minutes left, all right, I better speed up a wee bit then. We have been funded. We have a total of now 17 million, I believe, for 5 years. We have 9 million in capital funding from Western Economic Diversification, which we've used to buy a whole range of assembly and prototyping equipment so people can come in and develop prototypes, new products. And we have some operational funding to keep us going for the next few years. Luckily, we're independent from academia and government. We're able to act in an autonomous manner and really do what we think is right to develop successful commercial products. The senior management team will have about 20 years of relevant industrial experience, myself, Ken, and the other guys. And we have a managing board which comes from local industrial and finance communities. So again, we have that independence from academia and able to act in a way that really fits the commercial markets. We're easy to work with. We have a simple fee-for-service model. Typically we charge for equipment depreciation, which we work out over 5 years, charge out our manpower at cost. We're not for profits. We're not trying to make profits here. And the client pays for materials, consumables, any additional services we have to engage to make the project successful. And then if you're based in Western Canada, you can either get some very attractive grant funding from local funding agencies, and we're quite aware of all those, and we're actually a registered provider for a number of the funding programs, or we can give you some very attractive discounted rates because we're funded by local government. We don't want to take anybody's IP. That's one thing that we think sets us apart from a lot of the type of organisations we're similar to. The client gets to keep their own IP. We are manufacturers, so we understand our manufacturing processes, and we keep those so we can use them for anybody who wants to do manufacturing. We do both marketing and business development, and this is kind of the classic business development chart. I'm not going to walk through it in great detail. Ken can explain it at a later date. We do product development as well, and really our area of focus is assembly and packaging We believe very strongly in design for manufacturing. In other words, we take ideas and try and turn them into products that can be manufactured in the suitable volume to meet the demands of the end market. We're also very strongly into product tests. We've got to really prove that these products work before you release them to the end customer. We don't do any front-end fabrication, silicon fabrication or molecule fabrication, because that's already well covered in the region. And we use a lot of design, simulation, and verification to help people design better products. 1 minute to go. So very briefly then, a few other capabilities that might be of interest to people in the clean tech space. Lab on a chip. We have a full suite of tools, everything from ANSYS CFD, which can help you design a chip before you even try and build it, do a better design before you spend a lot of money building a chip. We can do all the mold making, and we actually have a hot embossing capability that lets you produce reasonable, moderate volumes of chips, maybe 100,000 units a year, up to that type of volume of chips. And we have a few other useful tools, like we can modify surface energy using plasmas and fun stuff like that. So, assembly and packaging, we can build modules, as I've pointed out, using our ceramic process. We can also build, these can be modules for remote sensors, gas detectors, pressure sensors, temperature sensors that can be introduced into all sorts of harsh environments, autonomous sensors as well. So we have a complete suite of tools to let us do that. We also are starting to build some useful supply chain relationships, particularly with one of the issues most of our customers find is actually obtaining die. So we're building relationships with some of the known good die suppliers, and TI is probably our lead vendor, but we're working with other companies like ADI and so on as well. And we've got a pretty robust, as I say, substrate process, good for 1,000 hours at 300 degrees C at least. In-house process capabilities, we've got a whole bunch of things we can do there. So the other thing I'd really like to bring out a little bit is our simulation and design capabilities. And we do a lot of front-end simulation and design work for people so they can test their products out in the simulation space before spending a lot of money manufacturing it. So we have ANSYS, who's probably the star tool at the moment. We have two facilities, one here in Calgary. The Calgary facility is primarily, Ken really wants me to get off the stage now, but it's primarily for early stage prototyping at the minute. We have a more manufacturing-oriented facility in Edmonton, which is capable of producing larger volumes. And so summary, we believe that it's a great technology and we can help you get stuff to market. Thank you.